This is a short video about paths in the complex plane. So our first definition, if I've got two real numbers, a and b, where a is less than b, a path is going to be a continuous function. We'll talk about what continuous means later. So gamma is the notation for our function here. And its domain is the interval of real numbers from a to b, so all numbers between a and b, including a and b, to the complex numbers. So notice, like gamma, you can think of it as a function. You input a real number, but it spits out a complex number. And so we should be able to write that down a little bit more formulaically, talk about its real part and its imaginary part. So gamma of t, that output, it's a complex number whose real part is f of t and whose imaginary part is g of t. And later on I'm going to show you a theorem that just tells us that f and g are continuous real-valued functions when we're dealing with a path. And so you can think of a path in the following way. So I'm assuming that if you've watching these videos, if you're watching these, then you've probably already had Calculus 3, in which case you talked about parametric curves and parametric equations. Or maybe you do that at the end of a Calc 2 book, like I know usually in Stewart. That's usually that last thing we get to in that book, Stewart's Calculus. Anyway, so if you want, you could think of x, the real part, that's f of t, and you can think of y as the imaginary part g of t. So I've just got these two parametric equations where x and y are both just some functions of t. And so maybe another word for path, you could think of it as we're just parameterizing a curve. And so this is some parameterization of a curve that this function gamma traces. Usually we'll refer to gamma, like the function, we'll refer to it as gamma, and also though, like the graph that it traces, we'll refer to that as gamma as well. So we'll kind of abuse notation there. So we'll call both things, the function and its graph, gamma. So let's look at some examples. So this first path, gamma sub 1, I'm using a subscript there. So gamma 1 is just t plus it squared, and I'm only looking at t between -2 and 2. And this traces out the familiar parabola y equals x squared. And I've got a little picture for you. So there's my parabola. And the way that it's written right now, there's nothing to indicate anything that's going on with the t's between -2 and 2. And so what we need to do then is draw that in. It's like, what happens, where are we when t is -2? Where are we on the parabola when t equals 0 and 2? And so to sketch that out for you, when t equals -2, you'd be at the complex number -2 plus 4i. In other words, if you want to think with parametric equations, you're at the point -2 comma 4. So remember, we're thinking about complex numbers also representing them as just regular two-dimensional coordinates like x comma y. Anyway, I see when t is -1, I'm at the complex number -1 plus i, and I just keep going around, and I see I end at the complex number 2 plus 4i, and that's when t equals 2. And so we would say that gamma 1 is one way that we might parameterize the curve y equals x squared. Let's look at another example. Let's say gamma 2 is the path minus t plus it squared, where t still goes from -2 to 2. That also is going to trace out your parabola y equals x squared, but the direction in which we go is reversed. And so here is my parabola, but now let's think about when I start at t equals -2, now I'm at the point 2 plus 4i. And notice now I'm going along kind of in the left direction. I'm going to the left as I go along the parabola until I end at the end point when t equals 2, I'm at the complex number -2 plus 4i. And so gamma 2, it still gives you that parabola. It's another way to parameterize this curve y equals x squared. You see they're different in the direction that we go. And so what are some things to notice just from these two examples? So first thing, paths, they have direction. Another word for direction is an orientation. There's supposed to be a parentheses ending that there, but for some reason there's not. So direction, another way to describe that is its orientation. So in my two examples, they have different orientations. And, oh, there's my parentheses. The second example, or the second thing that you should notice from these two examples is that a Cartesian curve like y equals x squared, there's lots of different ways to write down a path that still describes that curve. But again, how they might be different though is like the direction that you go, or maybe how fast you go along the curve. So those are some differences between, remember, parametric equations for a curve versus like a Cartesian equation for a curve. Let's look at one more example that we're going to encounter very often in a complex analysis class. This path gamma 1 of t is e to the it. And remember from maybe the polar coordinates video, what does this mean? You can think about that as cosine of t plus I sine of t. So the real part of e to the it is cosine of t, and the imaginary part of e to the it is sine of t. And so let's just consider t to go from 0 to 2 pi. And what you also might remember if you watched that video about polar coordinates is this was just a way to write down what the equation of the unit circle. And so this would be a path, we're saying the unit circle written down this way is a path. And when I draw its picture, it's going to have the counterclockwise orientation. And so I've just drawn a little bit of an indication about, we're going around that circle as t increases, we're going counterclockwise. So like when t is 0, we're at the complex number 1 plus 0i, in other words, just 1 comma 0. When t equals pi over 6, if you allow me to zoom in a little bit, we're at the point root 3 over 2 plus 1 half I, so that's when t is pi over 6, and etc. as I go around. Let's look at another example. Let's change it a teeny tiny bit from gamma 1. So now gamma 2 is e to the 2 pi it. And if I, again, write that out in terms of its real and its imaginary part, remember that's cosine of 2 pi t plus I sine of 2 pi t. And let's just consider t from 0 to 1 now. So instead of 0 to 2 pi, like the first example with the unit circle, let's do this. But this still traces the unit circle, and I still have the counterclockwise orientation. And now if I add in, some points as I go around to see where we're at, we see, for instance, like when t is 1/12, I'm at this point, root 3 over 2 plus 1 half I. And so what are we supposed to take away maybe from these two examples about the unit circle? There might be many paths to trace the same curve, even if you have the same orientation. So there's lots and lots of ways to describe a path. So maybe there's no unique way to describe a path is a stronger thing to say. Now what we want to do is we want to try to describe some of these functions. So above, I said a path by definition has to be continuous. Let's just talk about what does one of these functions being continuous even look like. What's continuous mean? So we're going to say that some function gamma from some real interval a to b to the complex numbers is continuous at some real number t0 if, and this should look a lot like what you encounter when you first encounter continuity in a calculus class. The limit as t goes to t0 of gamma t ought to just be gamma of t0. In other words, it ought to just be the output at t0, just like we're used to with any other definition of continuity. And here's a theorem. So if you've got a path, gamma, or if you've got maybe a function, perhaps I shouldn't use the word path here, since again, when you see path, you can take for granted it's continuous. But what's it mean to say that a function, gamma of t, that has a real part f of t and imaginary part g of t, what's it mean to say this function is continuous on an interval? Well, it's continuous on this interval if and only if both f and g are continuous functions on AB. So you just need to look at its components. So if you look at f and g and they are familiar functions to you from a calculus class, then you can take for granted that those are continuous. Because they are continuous because they are those functions from calculus class. We're just using them, as coordinates of a point. Another definition that's calculus related. We'll say that a function gamma from a to b into the complex numbers is differentiable at some number t0 that's strictly between a and b if the following number, gamma prime of t0, which is defined to be, remember that's the colon notation with the equal sign, so it's defined to be the limit as t goes to t0 of some kind of a difference quotient here, where I take the difference in the outputs above, gamma t minus gamma t0, divided by t minus t0. And so provided that this is a complex number, in other words, it exists and is a complex number, then we'll say that gamma is differentiable at t0. And what I want you to think about gamma prime of t0. And we want to think about it or visualize it as a vector that's tangent to the curve at that point t0. So kind of like you're used to in Calc 1 thinking about the derivative as being the slope of the tangent line, I want you to actually think now in this case of visualizing a vector that goes along the tangent line. And that'll be what gamma prime is. And it should point in the direction that we're traversing the curve. And now, how do I know if I've got, again, instead of path, maybe I should just use some function. If I've got some function that has the form f of t plus ig of t, how do I know by looking at it if it's differentiable? And it turns out it's going to be differentiable if and only if, you guessed it, f and g are each differentiable functions. And so in that case then, that also tells us I don't have to necessarily use that limit definition in order to take the derivative, in order to find gamma prime. Gamma prime just is going to be f prime of t plus ig prime of t. All right, so more definitions here. So a path gamma is smooth if gamma prime is continuous and non-zero. So let's talk about a way we should think about what smooth means, and then we'll do 2 examples about some functions that may or may not be smooth. So gamma prime, remember, you're supposed to think of it as a tangent vector to the curve gamma. And to say that gamma prime is continuous, I want you to think about it. That means that that tangent vector is turning continuously as you move along gamma. And to say that it's non-zero, that should mean that that vector, gamma prime, never has length 0, or maybe since this is a complex class, that complex number gamma prime never has absolute value or modulus 0. Again, if you've watched my videos, you've heard me use modulus, absolute value, and length pretty interchangeably. So let's look at some examples in order to understand what this definition says and how do I know if a particular path is smooth or not. So my first path to consider here is gamma 1, which is cosine of 2t plus I sine of 4t. And I'm considering it for t between 0 and pi. And I want to know, is it smooth and how come? So I've just got to check, is it continuous and is it never 0 as long as t is between 0 and pi? And so here's a picture of what gamma looks like, and then I also need to add in some numbers with orientation as you go around. And so what we're supposed to do is we're supposed to analyze gamma prime. And by the above, gamma prime, I just need to take the derivative of each of the components, of the real part and the imaginary part. And of course, by the chain rule, the first thing I see is the real part is going to be minus 2 sine of 2t, and the imaginary part is 4 cosine of 4t. And then what I've also done, just to try to emphasize what do I mean by a vector tangent to the curve at that point, I'm trying to draw you some values. So like when you plug in 0, you're at the complex number 1, right? But then you see that the vector that's tangent to the curve there points straight up. And so that'll be my tangent vector there. And just the things that I'm looking at, as you follow these blue vectors around what the red arrows indicate, I want you to just think about the blue vectors, they turn continuously. There's no really sharp turns. They don't abruptly change direction. And so in a picture, that's what you're looking for to try to justify in your head why it should be continuous. We'll talk about how to do it analytically in a minute. And the other thing that we want to think about in this picture, just based off the few blue vectors that I've drawn, by the way, not drawn to scale. They're not the actual length here of these vectors, but I'm never going to get the 0 vector at any one of these points. You're always going to have a vector with some length. So again, in my picture, I'm pretty sure that all of these tangent vectors will be non-zero. And so I'm thinking this curve is going to be smooth. But how do we do that analytically? So that's kind of the intuition, and now let's go analytically. So analytically, the first part here, when I look at gamma prime, I just need to look at the components, minus 2 sine of 2t and 4 cosine of 4t. I know that each of those individually are continuous functions, and therefore gamma prime is continuous. So continuous is good. So the next thing we've got to do is, are there any spots t where gamma prime of t is 0? And when I say 0, I mean, the complex number 0, or the origin, 0 plus 0i. And so what I need to do then is I'm going to try to set up a little system of equations to solve. And so to say that gamma 1 prime of t is 0 plus 0i, a complex number is 0 if and only if the real part is 0 and the imaginary part is 0. And so that is what I'm utilizing here. So in other words, 2 complex numbers are the same if and only if their real parts are the same and their imaginary parts are the same. So that'll always allow you to set up a little system of equations, and you'll see that logic applied over and over again in this class or in these videos. So what do we get? I need to think about, are there any t's that simultaneously make minus 2 sine of 2t and 4 cosine of 4t 0? And if I go through those, one way you could do it definitely is to graph, like graph on Desmos. You're only looking at t from 0 to 2 pi, so you can figure out if they ever touch the t-axis at the same time. Anyway, though, another way, again, continuing with this kind of algebraically, I know that, sine is going to be 0 at multiples of pi, and I know cosine is going to be 0 at odd multiples of pi over 2. So that allows me to set 2t equal to m pi, and 4t equal to 2n plus 1 pi over 2. And those are just for some integers m and n. So again, just utilizing what I know about those 2 trig functions. And in that case, that tells me if I solve each one for t simultaneously has to be m pi over 2 and 2n plus 1 pi over 4. And now, if you set those two things equal to each other and maybe multiply through by 4 and cancel the pi, you should end up with, and so here's where I've set them equal to each other, and now do that algebra. Try to multiply through by 4 and cancel the pi. You end up with 2m, an even number, equals 2n plus 1, an odd number, which of course is a contradiction. And so what did that show? That just showed that it was never the case that gamma prime of t is 0 plus 0i. So in other words, gamma prime is non-zero for all t in my interval, and remember that's the last thing you need to show in order for this path to be considered smooth. We just figured out it's non-zero. All right, so let's look at another example. So let's look at gamma 2 now, which is cosine cubed t plus I sine cubed t. And this should be for t between 0 and I think 2 pi is what I meant to have there. But this thing is not going to be smooth. So here's its picture. I think this is, it's got a name. I think it's called an asteroid if you take a trig class. But what are the problems? The problems about being smooth, it's kind of like what you think in a calculus class. We can't have sharp edges. And so I'm betting that these 4 corners are going to be the bad spots. And just for reference here, you know, my t's are 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I'm guessing those are going to be the bad spots. So let's go ahead and go through talking about why is it not smooth. You know, when I think about the derivative, and so I've computed it here, gamma 2 prime, I'm just using the chain rule to get that. And each of those components, the real part and the imaginary part, they're both continuous, so continuity is not the problem. Now let's talk about, is it possible that gamma 2 prime is 0 plus 0i? And in that case, remember, we're going to, if I set gamma 2 prime equal to 0 plus 0i in hopes for solving for any possible bad t's, I would set the real part equal to 0 and the imaginary part equal to 0 and solve this resulting little system down here. And in this case, when I look at the first equation, I know cosine is 0 at, again, odd multiples of pi over 2, and I know sine is 0 at any multiple of pi. And then similar, you get the exact, or you're going to use the exact same facts in the second equation below. So we recover all these values of t right here. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So we're just looking, these are the t's that make both of those equations 0 simultaneously. And so these are the t's where my function is not smooth. These are the t's where I have a tangent vector that has 0 length. In other words, the 0 vector is there. And so at these values of t, again, gamma prime is 0, really 0 plus 0i. And thus gamma 2 is not a smooth curve. Got a few more definitions here. So we're going to kind of loosen this requirement of being smooth. We could say that a curve gamma from AB to the complex numbers is piecewise smooth if there exist real numbers C1 through Cn such that A is less than C1 all the way blah 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 less than B. So it kind of looks like the definition of a partition so far, if you're familiar with that from like when we're thinking about integrating here. I'm just saying these numbers are between A and B and you're increasing until you get to B. Such that though, when I look at gamma on each of these subintervals, A1 to C1, C1 to C2, blah, 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 Cn to B, gamma is smooth on each one of these. So in other words, piecewise smooth is kind of what it sounds like. Your curve can be chopped into pieces that are smooth on those respective subintervals. So let's look at a quick example. So let's look at gamma that's defined in the following way. It's t minus it if t is between -2 and 0, and it's t plus it if t is between 0 and 2. I claim that this is piecewise smooth, and if you graph it, this is just the absolute value function from college algebra, if you like. And why is it piecewise smooth? Well, first of all, it's not smooth because of that cusp there at the origin. Cusp is another word for like a sharp turn. So I know sharp turns are bad as far as derivatives are concerned. So that cusp is no good. So it's not smooth, but I could think about this as having two pieces, and kind of like the formula suggests, right? If I think about the two pieces, gamma 1 really just being the top formula, that's just that line there. And don't worry so much about strictly less than 0. I just care about, is that smooth from -2 to 0? And the answer is yes, because it's a line. And the other piece would be gamma 2, I guess the portion of the line that's to the right, in the right half of the plane. And gamma 2 t plus it, that's also smooth there. So gamma is sort of the union of these two smooth curves. And so that is what it means again to say that gamma is piecewise smooth. A few more definitions. We'll say that a path is simple if it does not intersect itself, except possibly at the endpoints. So it's okay if it intersects itself at the endpoints, like at A and at B. And we'll say that a path is closed if gamma A is equal to gamma B. So notice, A is your starting number you plug in, and then B is your ending number. So it's closed if the initial point is the same as the end point, is what that says. Now let's do an example just to make sure we understand how these words work. So I've brought back in the unit circle, e to the it, from 0 to 2 pi. And the first thing I claim is that it's closed. And as you see, I am at the complex number 1 plus 0i whenever t is 0, but also whenever t is 2 pi. So gamma 0 is the same thing as gamma 2 pi. But it's also simple because, remember, what's it mean to be simple? The definition's right up there. The curve doesn't intersect itself except possibly at the endpoints. So the only time you're going to go around and touch itself again, that the curve's going to touch itself again, is t0 and t2 pi. Those are the only intersection points. So there's no other self-intersections. Therefore, the unit circle is a simple closed curve. And moreover, it's also smooth. So the unit circle is a fabulous curve. It's smooth, simple, and closed.